Okay, we are going to prove the following theorem, which claim over that region the harmonic function will have the conjugate. Okay, 2.30 theorem. Let's see. Okay, good. So we already noticed that not for every region uh, the harmonic conjugate exists, not. Okay, but for the following two types of regions, let G be either the whole complex plane C or some open disk if U from G to R is a real valued complex variable function is a harmonic function, then U has a harmonic conjugate. Okay, so over these two types of region, either whole complex plane or open disk. Complex plane is like the open disk with infinite radius. So basically, this is just one type, disks. Over disks, harmonic conjugate always exists. Okay. Okay, now let's see the proof. Let's see the proof. The disks, we can shift the disks. By shifting disks, we do not change the harmonic property. So without loss of generality, here we assume that G is the open disk centered at the origin with radius r. And here this r can be positive or infinity. It could be infinity. When it's infinity, it's a complex plane. And let U from G to R be a harmonic function. Be a harmonic function. Okay? Okay, so we're going to really construct the V and show that the VU satisfy the Cauchy-Riemann equation. Okay, so we define V of x. Okay, V of x. What is a V of x? V of x is a. Okay, let's see. V of x technically is V of y, Vx t dt and plus phi x. Okay, so just this. What is this? This is a fundamental theorem of calculus, right? You differentiate with respect to y, you integrate with respect to y, and from 0 to y, and usually if you check the fundamental theorem of calculus, you plus a constant, but here it has two variables. This is partial derivative, so this constant is a constant with respect to y. Any x function will be a constant with respect to y, so that's why you have such thing. But you know what? We don't have v, right? We don't have v in this argument, so this one does not make sense. What is this? What is this? We know eventually we want a harmonic conjugate. It means UV satisfy here. Vy is undefined, right? We don't have y prime. If we have y sorry, Vy. If we have Vy, we already know V. We don't have to define it, right? So V sub y is undefined, but since UV satisfy Cauchy-Riemann equations, in the Cauchy-Riemann equation, Ux is Vy. Ux is Vy. So what we get? We just plug in. So here, this is actually the reason why you see the following definition in the textbook. So we define Vxy equal to integral 0 to y Ux xt dt n plus phi x. U is given, so U sub x is known. U sub x is V sub y, so you have such a thing. All right, so that's a reason you directly have such definition, and why it looks like that. It makes sense this way. Okay, another one. Let's write the Uy is negative Vx, right? In other words, this if this V satisfy the UV satisfy the Cauchy-Riemann equation, this one is already used, so we have to check the second condition. Second condition, we get Vx then V sub x should be the partial x. It's not partial, it's a ddx. No, partial, my bad. Partial x integral 0 to y Ux xt dt and plus phi prime. Okay, you just differentiate two sides. And here we have the so-called Leibniz rule for differentiation. You can move it in. This is a Leibniz rule. For differentiation. Under the integral sign. Okay, the Leibniz rule for differentiation under the integral sign. Remember, what is the integral? Integral means the limit of the sum. The differentiation is also the limit. And x and y, they are independent. Technically, it just means you add along y first and differentiate along x, or you differentiate along x first and add along y second, the same thing. You can try to prove it. It's not that difficult. Okay, so we exchange the integration and the differentiation. We will get integral from 0 to y, and this becomes Ux x xt dt. Ux x xt dt, right? Okay, and this is exactly the well, no, it's just a Leibniz rule. And next we're going to apply the harmonic condition. U, where's U? U, yes, U is a harmonic function. What is harmonic? Uxx plus Uyy is equal to 0. And here you have Uxx. And integration is about y. They are independent. So you change Uxx to be negative Uyy. Right? You change Uxx to be negative Uyy. Move to the right side. And this is a differentiation integration along the same coordinate. Then by the integration, by the fundamental theorem of calculus, we know this is negative Uy x, y, this is antiderivative. Uyy has antiderivative uy. Minus uy x, you evaluate at 0. And plus phi prime of x. Right? And you distribute it, you will get uyy xy plus not uy, but uy xy plus uy x0 and plus y prime, phi prime of x equal to 0. In this process, what do? We don't know what phi is. We want to determine phi so that uv satisfy the Cauchy-Riemann equation. And Vx is negative uy. It's okay. So you must let this piece equal to 0. So you must have phi prime of x equal to negative uy x0. Phi prime is negative u sub y x0. And then phi x is integral negative 0 to, you see, we're going to integrate x. We're going to integrate x from 0 to x, uy s0 ds. We integrate about x coordinate. So we change the dummy index to be s. So this is a phi. Well, here we only need to find one harmonic conjugate, so we don't put plus c. So we don't put plus. And hence what we have, we have v xy is the integral from 0 to y u x t dt, and plus phi is plus a negative 0 to x u sub y s0 ds. And uv satisfy the Cauchy-Riemann equations. uv satisfy the Cauchy-Riemann equations. Right? So there's an issue. Okay, this is a finished proof. For all the disks, if the disk is not centered at the origin, you just shift it. Okay? So then we have a natural question. What condition makes this proof reasonable? Because if there's no condition for all the disks, for all the regions, this proof always works, then you don't have that counterexample, right? So what condition makes this proof reasonable? The condition is that for any point will be x plus iy. Any point in this G is R. Any point in this region G, the integrals, you have two integrals. The integrals need the segment from 0 to x and 0 to y. So basically, you have 0, you have x, y. You need to to be able to connect them. And when you connect them, you do the integral along this segment. All the points should make sense. All the points should make sense. Okay? By this way, we can go through it because the whole argument only depends on this connection, segment connection. Well, so that's the geometric property. But for G equal to C without 0, this condition does not hold, right? You can always find a point. You can for any base point. Here we choose base point as 0, 0. For any base point, assume this base point, this is another point. Then straight segment, you do integral along this line. This line, the integral over this line is undefined because of this point is missing, right? And also for this reason, actually we can generalize this proof to the so-called the star shape. Star shape region. What is a star shape region? Star shape region means there is a point A in G such that for any Z in G, the segment A to Z is contained in G, like this. You have this center and any other point you can connect, you can always connect. And whenever this happens, you can define the integral without a problem. You can define such integral, right? So star-shaped region is okay. Let me see if it's a star shape or shaped. Okay, this is shaped, star-shaped region. For this type of region, we can always do such trick. Okay, cool. Good. So we finish the section 2. This is the end of section 2. Now we start the section 3. Section 3, analytic functions as maps, Mobius transformations. Mappings, not maps, as mappings, Mobius transformations. Well, here the author gave the example about this idea. So they consider this simple function. Well, we already defined the general power function based on the logarithm, but for the integer power function, we still consider it as a z times z. So there's no branch. There's no branch for the integers. All right. Okay, for this, and we consider z as x plus iy, and mu plus I. What's this? This symbol. It's f of z. Well, let's see. It's a z squared x plus iy squared. It's x squared plus iy squared is minus y squared plus 2xyi. 2xyi. So we get mu as x squared minus y squared, and what's this? Is this symbol? It's a 2xy. 2xy. All right. So what we have? If we have in C, domain C, in the domain C, x squared minus y squared equal to a constant is a hyperbola. But its image is mu equal to C, mu equal to C, a vertical line, a vertical straight, a vertical straight line, right? And 2xy equal to d, this is again hyperbola. Its image is equal to d is a horizontal straight line. Horizontal straight line. Right? And we know that not we know that, you actually have to verify that this hyperbola and this hyperbola, they actually intersect with a right angle, intersect at a right angle. And those images, vertical straight line, horizontal straight line, they also intersect at the right angle. Yes? Okay, so it seems the angles are preserved by this the square function. By the square function. And we are going to show that this is not a special example. It's actually a general fact. The analytic function will preserve the angle. All right? The analytic function will preserve the angle. And another thing, let's see, this z is REI theta. Assume z is REI theta. The same function, f of z is z squared is r squared e2i theta. E2i theta. So if we have the region S alpha beta, which is a z alpha less than argument of z less than beta, so a sector. This is alpha, this is beta. It's a sector, right? And then F maps S onto this one, S of 2 alpha, 2 beta. Right? It maps S alpha beta to 2 alpha, 2 beta, because you multiply by 2. And it is 1 to 1. if beta minus alpha is less than pi. You cannot get two open. If it's not open, you will get a 1-to-1. And it is 1-to-1 if actually and only if beta minus alpha is less than pi. Okay, and beta will, if you get 1, 1, when theta is fixed, Fz is r squared e 2I theta, right? So, and then this part is fixed. You just only amplify or shrink the magnitude. So F maps raise to raise. F maps raise to raise. F maps the region to this region. It's 1-to-1 and onto under certain conditions. So there is a natural constant from here. You have one region to another region with a 1-to-1 and onto property. There's a, then from here we have a constant. Let G omega be two regions in C. Is there an analytic function f from G to C such that f of G is exactly omega? So can we have an analytic function between those two selected regions? Is there? Okay. So we want to get a mapping between those two given regions. Is this possible or not? Here, we just choose a square. But for the general open regions, do we need any conditions or not? Okay? So we will see the property of such questions. We will see the partial answer of such questions in this section. All right? Okay, so in order to discuss all these stuffs, let's start from the basic definition. Definition: a path in a region G in C is a continuous function gamma from AB to G for some interval AB in R. So this is an abstract path. Abstract path is determined by a continuous function. Okay? Every one continuous function give you a path. There's another continuous function will give you another path. Actually, you are going to imagine its image in the G, not just function. You're going to imagine the image. Okay, so if gamma prime of T, this is this continuous path. If gamma prime of T exists for each T in AB, then, sorry, not that, and gamma prime from AB to R, to C, no, my bad, to C. Gamma prime from AB to C is continuous. Then we call gamma is called or is said to be a smooth path. Okay, smooth in this case is continuously differentiable. continuously differentiable. Okay, so path is a definition path. This is a smooth path. It's continuously differentiable. You can have continuously differentiable. You can also have so-called piecewise smooth. Gamma is piecewise smooth if there is a partition of AB. Here A is equal to T0 less than T1 less than T sub n equal to B, such that gamma is smooth on each subintervals T sub j minus 1, T sub j. Here j is between 1 and n. So basically, what is piecewise smooth? Piecewise smooth means gamma is almost a smooth path, but with finitely many bad points. Finitely many bad points. Almost smooth, except finitely many bad points. Okay. All right. Now let's see. This is a path, smooth path, piecewise smooth path. And now let gamma from AB to certain region G be a smooth path. We have a smooth path, and T0 in the domain AB with gamma prime of T0 is not equal to 0. Okay, so we don't have a 0 complex number. This is a complex number 0. If you do not have a complex number 0, then gamma has a tangent line at what? At the point in G. AB, there's no tangent line. At the point in G, Z sub 0 equal to gamma of T0. So we have A, B, and T0 someplace here. And then we have the region, and this is a gamma A, this is a gamma B, it's a gamma T0, which is Z0. And the tangent line, this is tangent line with a direction. This line, this tangent line, this tangent line goes through the point Z0. You have to pass through this point in the direction of gamma prime of T sub 0. So this gamma prime T sub 0 actually gave us the direction. It contains the rate of change of x and it contains the rate of change of y, so that's exactly the direction of a line. Okay? And in other words, the slope of this tangent line is m equal to the tangent of the argument of gamma prime of T0. Tangent of the argument of gamma prime T0. Why? The y direction, why this is correct? The gamma prime T0 is actually x prime of T0 plus iy prime of T0. It's a parametric equations, right? Okay, and then you get what is the slope? Slope is dy dx. dy dx is a dy dt over dx dt, which is y prime x prime. Okay, so that's exactly y of x. That's a tangent of the argument. Correct? This is exactly equal to the tangent of argument. Not here, here. Right? This is the derivative. Okay, so we have the tangent. And when we have those, this is one thing. When we have two curves, two smooth paths may intersect at one point. This one is gamma 1, this is gamma 2, and we say if gamma 1 and gamma 2 are two smooth paths with gamma 1 over T1 is equal to gamma 2 over T2. So they are two smooth paths. They have two different parameters. So this is a gamma 1 over T1. This is also gamma 2 over T2. They both equal to Z0. And let's assume and gamma 1 prime of T1 is not equal to 0. Gamma 2 prime of T2 is not equal to 0. If it's equal to 0, 0 has no argument, so you cannot study the argument. 0, the denominator is 0, right? When this happens, then you see here that those two complex numbers will give us an angle. Then we define the angle between the path gamma 1 and gamma 2 at Z0 to be it's going to be the argument of gamma 2 prime T2 minus argument gamma 1 prime T1. So you just get that. This difference could be positive, could be negative. Or if you want a real positive number, just put opposite value. The difference, right? You just put opposite value, you will always get a positive angle. It doesn't matter. You get a positive, get a negative. It's not that important. Okay, so what is the angle? The angle between paths is just the difference of the argument of two paths, of two derivatives. All right, so this is okay, now let's see one thing. We will 39. Okay, let's continue. This is an angle between the path. We will come back to this after a few minutes. Suppose gamma is a smooth path. Gamma is smooth path in G. Okay, so AB to G. And G is a region in complex plane. So over G we can define function. And f from G to C is analytic. F from G to C is analytic. Then F compose gamma, sigma equal to F compose gamma, is also a smooth path by the chain rule plus composition of continuous maps. Okay, so this is also a smooth path, and the chain rule tells us gamma prime is f prime of gamma of t times gamma prime of t. Sigma prime is f prime of gamma of t times gamma prime of t. Right? So if we have a b t0 and g gamma of t0, f, let's call it z sub 0, f of z0. Okay, so let z sub 0 be gamma of t0, and suppose gamma prime of t0 is not equal to 0. F prime of z0 is not equal to 0. Then it is a product. This one is not 0, this one is not 0. Then sigma prime of t0 is not equal to 0. You have three numbers, they are all non-zero. They are all non-zero. And the argument of sigma prime of t sub 0 is equal to the argument f prime of z0 plus the argument gamma prime of t0. Okay, so let's check. In this one, we move to the left side, so we get the argument sigma prime of t0 minus argument gamma prime, sigma prime t0 minus argument gamma prime t0 is equal to the argument f prime of z0. Okay, so what is the importance of this formula? This formula is important. The importance of this formula is the following. This part, you have a two path, right? You have two paths. This is one part. They have two paths. Second part. In this part, it only depends on this function and this f. It actually does not depend on this path information. There's many paths through these pairs. This z0, and possibly you can call this as w0, whatever, right? This information only depends on f and its derivative. So it's a fixed independence of those pairs of curves. So now let's see. Here we have one version, one step version. Let's see another version. So let gamma 1 and gamma 2 be smooth paths. Okay, this is gamma 1, gamma 2. They have intersection with gamma 1 of t1 is equal to gamma 2 of t2 is equal to z0. They overlap at the same point z0. And of course, we require gamma 1 prime of t1 is not equal to 0. It's not equal to gamma 2 prime of t2. And for each of them, this go up and go down. This is a sigma 1. And this is a sigma 2. sigma 1 is F compose gamma 1, sigma 2 is F compose gamma 2. And this is Z0, of course, here is F of Z0. Okay, so we let sigma 1 F compose gamma 1, sigma 2 F compose gamma 2. That's what I said, they're independent, right? You have a pair of a different pair. Second, we assume they do intersect. That's up. We assume that gamma 1 prime of T1 is not equal to gamma 2 prime of T2. They do have intersection. They're not tangent, not like this. Not like this. We don't want this. This actually means the same thing. One stuff. Okay? It's if you tangent, you are actually in the local part, you only see one thing. You don't see the other thing. Okay, gamma 1 prime T1 is not equal to gamma 2 prime T2. Then what we have? We just apply this observation. We apply this observation, we get argument sigma 1 prime of T1 minus argument gamma 1 prime of T1 is equal to argument sigma 2 prime of T2 minus argument gamma 2 prime of T2. Right? They are both equal to argument of F prime Z0 because this is a fixed thing. F and Z0, they are independent of those two pairs of curves, so it's fixed. And then I'm trying to put what? Put sigma together on the left-hand side, gamma on the right side. So we get argument sigma prime of T1 minus argument sigma 2 prime of T2. Here it becomes argument gamma 1 prime T1 minus argument gamma 2 prime of T2. Exchange those two terms. Then what this is? This, by our definition, you see you have gamma 1, gamma 2 primes. This is exactly the angle between curves, between smooth paths. This is the angle between smooth paths. So this is the angle between the pre-image path. This is angle, this is pre-image. When we say pre-image or image, we're talking about F. This is the image of F. Right? So the angle between the pre-image of F is equal to the angle between the image of F. It means F preserve the angles. F preserve the angles. So the angle between the curves between the smooth path are preserved both in magnitude and the direction. Magnitude and direction, if we put ups value, that's magnitude. Without the ups value, you have plus minus sign. So that's what they say, magnitude and the direction. Okay? Okay, so that is the proof of the theorem 3.4. If f from G to C is analytic, we need analyticity, not just differentiability, because analyticity contains continuity. So with the continuity, sigma will be continuously differentiable. Okay, so far we need analyticity. Then f preserves angles at each point z0 of G, where f prime of z0 is not equal to 0. Why? Why do we need this? We don't see it in the argument. Actually, we use it. We have this equality. It is equal to they are equal to the argument of f prime of z0. If this is 0, there's no argument, so you cannot set up the equality. So that's why you must have this condition. Even though it looks like you don't have it in the proof, but actually you just didn't write it down. Okay? So that is the theorem 3.4. Analytic functions will preserve angles at the point where the derivative is not equal to 0. It's not equal to 0. Okay? So this is a geometric property. This is a geometric property. So we will see that a function f from G to C, which has the angle preserving property. You have to preserve the angle, and also has the limit z approaches a, ups value of fz minus fa over ups value z minus a existing is called a conformal map. Okay, so that's a definition. Angle preserving plus existence of this limit, magnitude existence, limit of magnitude ratio exists. That's called conformal map. And we can see that if f is analytic and f prime of z is not equal to 0, for any z, then f is conformal. Right? So analytic functions is a conformal map. It's a conformal map. It's a mapping. It's a map. It preserves the angles. And in the future argument, you may see that conformal map is another name for the analytic functions. All the conformal maps must be an analytic function. So this is another equivalent statement, but we may not have time to prove that in the future. Okay? Okay, so we don't finish this the lecture yet. We will continue in the next short video. Okay? So let's stop here and continue the next one. Thank you.